Hello, this is example 7, and this one is a little bit confusing, and I found it a little weird. But it's following what was shown. There's a force, the M1 force right here is pulling down while M2 is going up, and of course the force applied to M1 that's going down is mg, and the force going up is t. So going up, we have the acceleration and also the tension. Actually, I don't know if M1 is going up or if I think M2 is going down. I'm sorry. And then we get the two equations, which is T minus M1G equals M1A, and we have M2G minus T equals M2A. Um, the into the M2G becomes a positive rather than negative because I believe it's going down, and that's the direction that we chose to have. In order to solve this example, we just need to find t and we need to find a and t. So we start with the equation m1g plus m1a equals t, and then we just plug in the values. So 10 times 10 plus 10 times 90 over 110 times 10. And from that, we get an equation for tension. And then applying here this rule with both the systems, we get A equals M2 minus M1G, and then we get M1 plus M2, over M1 plus M2 right here. And so we're able to isolate acceleration and find it. And then for tension, we have the equation tension equals M1A plus M1G. And solving the equation, plugging in everything, we get 81 to the 8th power plus 100, and that's 180. And then we have M2G minus M2A equals T, and plugging in, we have 100 times 10 minus 100 times 8 to the 18, and we get a negative same value. So which the force should be equal. On one side it's going down while the other side is going up. So yeah, that's example. All right, so this is the one of the exercises of work and energy. So we have an object with has a velocity of 10 meters per second, and mass is 1 kilogram. And after some distance, the object has 1 kilogram, and the velocity changed to 100 meters per second. So the first question says, what is the work done on the particle? So here we start. So we have basic things that we have. We have the velocity here that that has a mass of 1 kilogram, and that after some distance, the velocity increases to 100 meters per second. We don't know the distance, but we know that there is a work done to change the acceleration here. So the velocity here. So we do the simple equation where work is equal to the change in kinetic energy right here, and then we obviously it's kinetic energy final minus kinetic energy initial, which is equal to the formula, 1 over 2 mv2. So we get the final one minus the initial one, and then we have to plug in the numbers. This is the final velocity, this is the initial velocity, and if solving this equation, we get that the work is over 0 because obviously there's positive work. The velocity changed to a higher velocity. So then we find that it's 5,000. The second exercise says, can you know what the force that makes this? The answer is no, we cannot. We know that the force that we know that the work, right? the force times this distance, we know that the work is 5,000, but and we know that the force is in the direction of the displacement, but we don't know what the displacement is. C says, can you tell me the distance traveled by the body? This is also a no. The force by the displacement. By displacement is 5,000, but not the distance that it traveled. So you can only it tells the work, the amount that made the change in velocity to higher velocity, but it does not change, but it does not tell the distance. And D says, what does it mean that the object has kinetic energy of 5,000 joules? So 5,000 joules just simply mean that there's the object that has the 5,000 joules, and the energy comes from different places. It could be 1,000 here, 1,000 here, 1,000 here, 1,000 here, 1,000 here. So it could be 5 meters and 1,000 newtons. So here we see some examples, like right here we have 5,000 newtons times a meter, and we get 5,000 joules. And here we have the opposite. We have 1 newton, but in displacement of 5,000, and that is equal to 5,000 joules. So it can be different examples. This could be 500, and this here could be I don't know, we could do 50, 50, 50, 50, and eventually it's 50 times 10, so we do like 10, so 50, another 50, another 50, and that's the whole concept of this exercise right here. Hello. This is an example from work and energy. It says a particle mass m start at rest and move vertical distance in the, I don't know what's written there, of a gravitational field F equals minus mg. And then we have the questions. We have A. It says find the work done by the force F equals minus mg. I think that's a final. Going to y1 equals 10m to y2 equals 6m. Alright, so the first one is basically pretty simple. We just imagine this situation here where, it's going up by 10, and this is going up by 6, and this distance here, the displacement is going downwards, as well as the weight, as well as mg. So we can establish the relationship that work is equal to the force in the direction of the displacement times the displacement, which is equal to mg, right? Mg, same direction right here. Mg 4. No, sorry, 4. Sorry, what am I thinking? Mg y. This is a y. And w, we've seen that work is greater than 0 in this case. So going to B, it says find the velocity of v, the magnitude of v from y equals 6 meters. So we established the equation that also w is equal to the change in the kinetic energy. So this is going to be greater than 0. It's always greater than 0, by the way, the kinetic energy. And it says mgy. So we established the equation mgy, which is the same thing as the work. Same thing right here. We established that mgy is the same thing as the work, equals half m v to the second power times 6, which 6 was one of the values that it told us right here. 6 minus half mv to the second power times 10. But this is not what it's asking, so we kind of ignore that right now. So the weight is 2. I mean, the mass is 2. The g, we already know what that is, and then we have y here. So that is going to be equal to the velocity. Is this a 4 or what? And then equals velocity times, to the second power times 6, which is the number that we have here. The y is equal to 6. And that we established after this equation, we see that the velocity squared is equal to 9 meters per second. So going into C says generalize the equation for any given delta y. So the equation that's going to serve for everything is that mg times the displacement in y is going to be equal to half m times v squared final, right? Just like like in this case. And we can also tell that v squared final is going to be equal to 2 times g times the magnitude of delta y. Then we go into D. It says find the potential energy associated to the force F equals minus mg. So in order to find the potential energy, we start by drawing the equation. We're just trying to prove that F is equal to minus mg final, and the work is equal to mgy. So it's gonna be work equals to minus the displacement work and u, and it's gonna be work equals u times a minus u times b. It's a direction going downwards, and we established that work is already greater than 0. Then y1 is going to be greater than y2, and y1 minus y2 is going to be greater than 0. The work then is going to be mg y1 minus y2, right? Get it from here. From here. And that's going to be equal to u times y1 minus u times y2. Then work from y1 is equal to mg y1 plus 1. And then we have these two equations, just u, this is a u, by the way, u times y to the second line is going to be equal to mg y2 plus, I think this is, let's see. And we establish from this equation here that u times y1 minus u times y2 can be equal to mg times y1 minus y2. So we can draw from this, we go to this right here. So uy times y equals to mgy plus c. And then it goes here, mg, this kind of proves this point, right, by the way. This refers to this. So mgy1 minus mgy2 equals to u times y1 minus u times y2. So that basically answers how to find the potential energy. And now establish the principal conversation of mechanical energy. So the principle starts from this. Work is the change in kinetic energy, which is opposite to the potential energy. And we have kinetic final minus kinetic initial equals to u. This is supposed to be u initial times minus u final, because it's opposites. So from this we can draw that kinetic final. No, this is the same thing as this right here, but the difference is that we just play around with it, and the u f goes to the other side while this one goes to the other side. So this is going to be kinetic final plus potential final equals to kinetic initial plus potential initial. And then just playing the formulas of both, we get this equation right here that establishes the principle of conservation. There we go. Hello, this is my second attempt to record this exercise. So this is example 4, the first one of the Newton laws notes. So you do this exercise asking to find the tensions in equilibrium, where A is equal to 0, y acceleration is equal to 0. We have these measures right here that we're going to use to solve the exercise. And then we have the steps, which is isolate the body, choose a positive direction. Oh, sorry. What is this? Sorry. Choose a positive direction as the acceleration. Draw all forces acting on the body. Choose system of reference. See the components fx and fy. Then apply fx equals max and fy equals may. So here are the steps. So first, since a is equal to 0, then the sum of all the forces in the x direction and also in the y direction is going to have to be 0. So first step is to isolate the body. So we have T3, and then we have mg going the downward direction, and T3 going in the up direction. We determine that they're both equal to each other because the acceleration is equal to 0. But we also need to find T1 and T2, which are in the x direction. So we isolate the point. We have T1 here, we have T2 here, and then we have the angles theta and theta 2. And then there's T3 here, which has to do with the y direction. So we use these two equations to solve the exercise. So here we have the first equation, which is the sum of all the forces in the x direction is equal to T2 cosine of theta 2 minus T1 cosine of theta 1, which is equal to 0 because, we determined that it was equal to 0 right here. Then we have, in the y direction, we have mg minus T2 sine of theta 2 minus T1 sine of theta 1 equals 0. The cosine, by the way, comes from the x direction, and the sine direction comes from the y direction. And also mg is positive because it determined that the direction of mg should be positive, and the direction of T2, which is the direction upwards, should be negative. So both of them are negative. And then we arrive to the algebra of it. So we got the two equations here, and we just plugged in the numbers. I'm sorry, just plugged in the numbers, and yeah. Then we have this system of equations. We have these two equations: the equation for y right here and the equation for x right here. And then we just use algebra to solve these equations. We just, for the x part, we just make them equal to each other and then solve the equation right here. And then for the y, we just, it's a little bit more complex, but it's also not that hard. So, yeah, you follow the algebra here and you just get the result right here. That's basically it. What is up, my people? So here's example. I don't even know which example, like the number, but it's this one right here. This one. Say we have that an object moved from point A to point B. So right, I have point A here, I have point B here. So it asks, here's a displacement. So it asks, what is the work done by N? So here we start the exercise. We know that N times the, N is basically the force times the displacement. This is going to be equal to 0. W, right, work is going to be equal to 0. And as always perpendicular to the vector displacement. So as we see here, right here in the image, it's perpendicular to the displacement. So yeah, work's gonna be 0. I think that's what asks, right? Yeah, the work's gonna be 0. What is the work done by F equals minus mg? So we have the mg in this direction right here. We have displacement right here, right? It's going from here to here. It's a diagonal displacement. Then we have mg, we have, you know, delta x with delta y. That's the displacement. That's how you calculate the displacement going in this direction here. So we have work equals to mg here, the force, and we have the delta x, and then we have the delta y to deal with right here. And then work is going to be equals to 0. Right, we already saw that the work is 0 when it comes to the x direction. So when it comes to here, because n is always perpendicular to the vector displacement. And then it's going to be plus mg y1 minus times y1 minus y2. And that's how you calculate f, this portion f equals minus mg in the, I think it's the y direction, the j direction actually. What is the speed at point B? The speed at point B is calculated here. W net is going to be equal to work n plus work mg. Work n is already 0, so we're just going to have mg times y1 minus y2, which is the displacement. And work net equals the kinetic energy, the change in kinetic energy. And then we have the work net that we already got from here, which is this one. So we have it here equals to this formula, right? 1 over 2 mv to the second power final minus that initial. And if y2 is equal to 0, then we have this. And if velocity is equal to 1, velocity is equal to 0, we have this. Just take a time to look at it. Now mgy equals half of m times v2 final minus 1/2 mv initial to the second power. And if velocity is 0, then we have mgy equals half of m times v2 final. And then just by solving this is algebra right here, we get that v2 is equal to the square root of it's going to be 2gy, and that's how you calculate the speed at point B, which is this one when it hits the ground. Thank you. Hello. So here's example 6. Mass is 2 kilograms. Theta is 30 degrees, and we have the magnitude of F, the force at 15 newtons. So the first exercise is to find the acceleration to parallel to the plane. So it'd be like this acceleration. Say, in order to solve this, we have to basically draw first and analyze. We determine that the sum of all the forces is mg, right? This right here, mg, times sine of theta, because it's this degree, right? It's an angle in this direction. So we decided to have that direction as a positive, so it's going to be mg times sine of theta minus f equals ma. So we get rid of the m already, and we're left with g sine of theta minus f equals a. And then we just plug in the numbers. So here we have that gravity is 10 already. And then sine of theta is half. And the force right here is 15. So we make it equal to A. And we solve for A, and we get that A is negative 10. So it is moving in the downward direction at negative 10 meters per second square. And then in order to find B says find the force that you would need to apply in order to have a parallel, like the force parallel to the plane equals to 0, which means it's at equilibrium, right? Which means that V is constant. So it would be f of x equals ma equals 0. So it'd be 0 because even though mass is not 0, but acceleration is 0, which makes it equal to 0. And then we just it's just the sum of the forces. So we have plus 5 from this equation, right? Minus 15, plus F, and then we just solve for F to find the force needed to be able to have an equilibrium, which it'd be equal to 0 at the end. Thank you. What is up, ladies and gentlemen? This example says a man moves vertically an object of mass m equals 5 kilograms. A distance change in y equals plus 2m with constant speed. And then it says A, what is the total work? B says, what is the total work done by the man? What is the total work done by the weight? Say we have here basically the object, and the object, the displacement, we see that it's 2 meters, right? It says it right here, right here. And it says that the mass equal to 5 kg. So the W net should be equal to the change in the kinetic energy. And so if we do it by going up, sorry, let me do it in a different one. Let me do it by going up, then we see that the velocity is going to be in this direction. Well, we have mg here, and we have also mg here, and displacement is obviously going to happen in the up direction. So a is going to be equal to 0. Then v, since v is constant, then we can draw these equations. We can draw this since the work is done when it's going up. It's positive. It's more than 0. Then it's going to be mg times y2 minus y1, and that's the work in the up direction. Now the downwards direction, since this is going up, this is going to be negative. It's going to be less than 0, so it's going to be equals to minus mg times y2 minus y1, which is obviously the displacement. Going downwards is basically the same thing. You have your displacement that's going down. You have the velocity, which is also going down, which is constant, so acceleration is 0. And now you have the force mg, you have the force mg right here. So the work in the upwards direction is going to be, now it's going to be negative. Why? Because it's going downwards. So it's going to be minus mg times y1 minus y2. And this is work in the downwards direction is going to be positive. So it's going to be mg times y1 minus y2, which is bigger than 0. Sorry. Then the net is just putting the equations together. That brings up a 0 right here. And that's basically it. All right, so here's an example with the elevator. So it says a man of mass m equals 80 kilograms is at the elevator. He stands up on a weight scale. Find the measure on the weight scale if the elevator is moving up at v constant, moving down at v constant, moving up at ay equals 4m at 4ms, and then moving down at ay equals negative 4 meters per second square. So we're not doing these ones. They're basically the same thing as D, C, A, and B. And here's how we do them. So we imagine there's an elevator right here with the two forces, right? We have the force N, we have the force mg, which is the weight, and then we have the acceleration. Acceleration is 0, right, when v is constant. So for A and B, we find that obviously there's the guy here, and then there's mg pulling him down, and then there's the force N to bring him up, and then there's force equals ma, which is the equation, and the sum of the equations is going to be plus n, which we chose n to be the positive direction, and then mg to be the negative direction, and then n minus mg equals ma. But we know that acceleration is 0, so that means that n is equal to mg, and that's going to be the case for both A and both B. Then for C, we imagine there's a force N up. There's an acceleration moving the elevator up, and there's mg, which is not as big as the N in this case. So we settle that N is going to be in the positive direction and mg in the negative direction. So equals ma, and then N equals mg plus ma, and we have the measure. The guy weighs 80, and it's going to be 80 times 10, which is, this gravity, plus 80 times 4. And then we have it's 1,120 newtons in the up direction. For G, for D, we have mg is a bigger force, and then we have N, and then we have A. So we can choose mg to be in the positive direction and N to be in the negative direction. It really doesn't matter. Equals ma. So I chose mg and ma to be in the positive direction, while N in the negative. So here we're gonna have mg minus N equals ma, and then mg equals ma plus N, and then I have 100 equals 80 times 4. Since it's in the positive, I chose A to be in the positive direction, so this is for positive. So N is gonna be for 80 newtons in the positive and the up direction. So since mg is higher, and this is gonna produce an acceleration that's gonna be negative in the just in the downward direction, basically. All right, so this is example 9 of Newton laws. So we have to find A2, T1, T2. So in order to find that, the mass of the rope, says that it's 0. So there's no friction. We start by these are the equations that are given to solve at the end. So in order to arrive, I'm just gonna do a video on how to arrive on that. So we have the equation T, right? We have a force. We have T. We have mg, and then here we also have the same thing. We have T, and we have the weight mg attached to this rope. So the equation is going to be T minus mg sine of theta, because of this, right? We're talking about this one. Equals m1a. And we have another equation, which is m2g minus T equals m2a. m2g, that's in the positive direction. Then minus T, right? T is against it right here, equals m2 times acceleration. So we get the equation m2g. If we combine these two equations, we get m2g minus m1g sine of theta equals m1 plus m2 times a. We get this. So we're able to get this, and this becomes this equation to solve for A. For T, it's basically the same thing. We get T equals m1a plus mg sine of theta. T is also equal to m2g minus m2a. That's for the second equation. That's for the first one. And then combining these two equations, we're able to arrive to these equations to solve for T. And then for these equations, we just plug in the numbers, plug in numbers and solve the equation. There we go. All right, so this is a problem of conservation of energy. So we have this example here, has a spring. The displacement in x is equal to this, m is equal to this, and k is equal to this. So it's asking us to find the maximum height. So according to the conservation of conservation of mechanical energy, we have energy of mechanical A is equal to energy of mechanical B. So this we put this into formulas. It's going to be 1/2 times m to the velocity to the second power in A, point A, plus mgha plus half of kinetic times x to the second power, and that is going to be equal to half mv to the second power b plus mghb, and this is going to be plus the 0 right here. This is going to be a 0. We're not going to need this. So we've seen that the kinetic energy for A, there's no kinetic energy, so this is going to be a 0. mgh, there's this also 0. Because I think it's because there's no height at point A, right? Yeah. So we're left with this, which is equal to this is also going to be 0. There's no kinetic energy, but there is a height in this. There is this is not going to be 0, so it's basically going to be this value equal to this value here. So hb is equal to, we're solving for height, so when we put them together, height's going to be a half times k to the times x to the second power over mg. Height's going to be, if we just plug in the numbers from here that we have here, we're going to obtain this value. hb equals 10 to the third power times 7 times 10 to the negative second power, and that's going to be over 1 times 10. And calculating this is algebra. We find the height at the point B, which is what we want to find. It's going to be equal to 1/4, and that is translated to 0.25 meters. Thank you. All right, so we have this second example here. So we have the point A right here, and we have the point B right here. Point A is at the floor. Notice this is at the floor, so no, if anything, height here is 0. So it's asking to find the maximum elongation. This is spring. I think it's what's called a spring right here. And it's asking for the elongation. So there we go, right here. So the principle of conservation of energy states basically this equation. So it's half mv to the second power, that's kinetic, plus mgha plus half of kinetic of k x to the second power a, and that's going to be equal to everything else here but with a point B. So I'm assuming that V is equal to 10 meters per second, K is 1 and M divided by M, and M is just 1 kilogram. Then we have this equation where half of 1, which is M, times 10, which is velocity, to the second power, plus 0. This is 0 because it's at the floor right here. It's at the floor. Which is plus 0 because there's no compression here. So it's going to be equals to 0. There's no kinetic energy. Plus mghb. There is a mghb because we're assuming it's at the floor and it's right here. So there is a height. That's what we're trying to find. Oh, sorry, it's the maximum elongation. Never mind. But there is mghb on plus 1, 1/2. On this one there is compression here. You see, it's compressed. So we have this, which is a half k times hb to the second power, and then plugging in the numbers, solving this becomes 50, which is going to be equal to 1, right? 1 times 10 times hb, which we don't know hb yet, and that's what we're trying to solve, plus half hb to the second, because k is equal to 1 n over m, and then we have to multiply this by 2, and we get 100 equals 20 hb plus hb, right? We multiply by 2 because of this, so we get rid of the fraction here, and then we just have a quadratic equation, and then solving this quadratic equation, that's the number we get. Thank you so much.